So, and then we're going to give you a few words of summary of what I told you. And as you'll see, there are two major milestones in the advancement to the beta plane. It's not that simple. So let's start with the 120-year-old theory by Ekman in 1905. This is the thesis is submitted to the University of Uppsala. And what you can see here is that the title of the paper of this thesis is precisely the title of his published paper, and these are the actual equations from his paper. And as you see, this is exactly what we use today. Actually, you and I have used it not too long ago. And this is the wind stress, okay? So this is the wind stress that applies. This is the F-plane. So on the F-plane, there is no preferred direction. Okay? All directions are identical. You can move north, south, east, west. It doesn't make any difference. And what he writes, what we'll do first is look at what happens in the steady solution. And in that case, you see that he worked on it. He was probably between 1902 and 1905 that he actually developed the theory. He mentions the 1902 cruise by Nansen, by the way, the only oceanographer to receive a Nobel Prize. Nansen, right? The Peace Prize. Nobel Prize, I didn't say for what. Nobel Prize for peace. He became a diplomat after having been an oceanographer for a few years and got his Nobel Prize for peace. Going back to our century, you see that he realized that the wind, direction of the wind and direction of the icebergs or the ship they are deflected. They are not in the same direction. So he knew both, and he went ahead and solved it. And it's a beautiful, when you read his paper, those of us who know what the graph paper is, it's really something that most people here don't know what the graph paper is. Am I right? Okay. Okay, in any event, this is a graph paper. And he used it's what? Right. In any event, this is his approximate solution, not approximate, what he computed, his computed solution. And this is what you see today in textbooks, just modern rendition with a little more color and more arrows, etc. You know, it's a projection, but you see the projection here is precisely what Ekman himself envisioned. This gives rise to the Ekman spiral, which we're not going to talk about. We're going to concentrate on the transport. So when you integrate from a certain depth below which the wind doesn't apply anymore, is not felt anymore, so you have a column of water pushed by the wind, and of course, once it's getting into a motion, there is also Coriolis force, and somehow the trajectory of that column of water is set as a balance between the wind forcing from above and the Coriolis force that's inherent to its own motion. And this is, I think, from the UK Open University. No, you recognize it? You don't know. Oh, I'm sorry. I thought you were an oceanographer. Okay, so the idea is that we know that there is a steady solution that goes this way. Okay, that's 90 degrees to the direction of the wind. And the reason it goes 90 degrees because the Coriolis force associated with this motion is directed another 90 degrees from the direction of the flow of the water, which is exactly 180 degrees from the wind stress. So the two can balance each other, and we have an exact balance between the two forces. And the question is what happens to it on the beta plane, and how we combine the time-dependent solution. If I spoke about the time-independent solution, now the steady solution, how to combine the two. And Ekman himself, reproduced here in Gild's book, knew how to add the one and one together and get two, and not like many of us do, get three or 1.5. You know, sometimes it's a little confusing, 1 + 1. So in the case of a westerly wind or eastward directed wind stress, you have a steady solution that goes that way, and it is compounded by, this is the steady solution. It is compounded by inertial oscillation. And since f, the Coriolis parameter, Coriolis frequency is constant, the frequency of those oscillations is precisely the frequency of the local Coriolis frequency, which is f0. And the two are combined together so as to start with, say, initial velocity at time equals 0, the velocity at time equals 0 being 0. Because if you start with 0 initial conditions, just combine the two and you get this cycloid. So, and clearly this solution has nothing to do with the longitude. In the case of, again, a zonally directed, eastward directed wind stress, the motion of the column of water doesn't know it all about the longitude. It goes back and forth and just completes those inertial oscillations, but actually doesn't move, again, on average, either westward or eastward. So the question is, how does it change when we come to the beta plane? So these are the equations, okay, that Ekman himself studied. You know, this is just the definition of U as the rate of change of the x coordinate, and this is the rate of change of the y coordinate, the north-south. This is the momentum equation in the x direction. Remember that we have a wind stress operating there, and we don't have a wind stress operating in the north-south direction. So these are just the momentum equations, what we call. This is what? Yes, the way I wrote it is a little, it's vertically integrated, but in a minute I'll go to the vertically average by introducing an H here. But allow me to skip those details. It's fine, okay. Okay, so again, when f is constant, then all coefficients are constant, and the solutions can be added together. We can just add the solution, the steady and the time dependent. And this fourth order equation can be easily solved, of course, numerically. So what we want to do is we want to add beta y to the definition of the Coriolis frequency. Okay, so this is the idea. What happens? What question is what happens on the beta plane? So from the beginning, what we can anticipate insofar as complications are that first of all, when we add beta y to f0, there has to be a certain point in y in which f vanishes. Okay? That point is the equator, right? If you just solve this linear equation, even I can do it. I mean, Bill doesn't admit it, but I can do it. At this latitude, the Coriolis frequency completely vanishes, so we suddenly have an equator. And on the equator, we know that there has to be a simple, if you will, the simple second law of motion, Newton's second law of motion. We have a force in this direction. The force is uniform, doesn't change with time or space. Therefore, the acceleration is uniform. Therefore, the velocity is linear, and therefore the displacement is quadratic, and that's it. No more to talk about. So this is an additional complication. We have to wrestle with it somehow. And the other complication is that we have to account for the transition from the mid-latitude, which is Ekman's solution, to that on the equator. So when does it happen, and what time? At what time will it set in? And there is another complication, which is the nonlinear. Oops, what do they do with the nonlinearities? Didn't talk about it yet. Okay, in a minute it will become clear. So some of the issues we can anticipate very sensibly by just looking at the solution of the F-plane solution, the solution of the F-plane equation. So for example, you know that in the steady solution, F appears in the denominator. Yes? Not yet, not yet. It's the same, because the term that's not constant doesn't depend on t, but on y, which is a dependent variable, hence nonlinearity. Yeah, wow. Ah. But he was talking about steady. Yeah. Right. Right. No, because it's W. Let's leave it to the end. Okay, the other thing is that the frequency of oscillation obviously changes because you change F. Because so I said there is a steady solution that's affected by F. There is a time-dependent solution whose frequency is determined by F. So if you change F, you might expect that the frequency will change. And with the change in frequency, you also have a change in the amplitude of oscillations because the action or energy flux or omega times a squared, the frequency times the amplitude squared, has to be constant. And therefore, we anticipate that both the frequency will change and the oscillation's amplitude. And again, we don't know anything about the inertial dynamics, so the only thing we can intuit about is that perhaps what happens is that inertial oscillations, okay, if you extend inertial oscillations from the F plane to the beta plane, then they start drifting westward. So we might say, okay, so this will drift westward like inertial oscillations, but the question is what happens with the wind stress? The wind stress can be directed either eastward or westward. So how do these inertial oscillations combine with the natural oscillations? So obviously to integrate the equations is very simple. Bill, even I can do it. A secret. Usually my students do it, but even I can do it. Okay. So the idea is that if you look a little, so this is, for example, what happens when the wind stress is directed eastward. Okay, so it's positive. And what you see in blue are the F-plane trajectories. And you see the blue oscillations as exactly as in Gill's book. Okay, so they just start, again, we start with zero initial conditions, and they reach up to here. If you look at the beta plane, for beta plane is tuned around 30 degrees or so, the value of beta. So you see that they extend a little further if you complete it. So they move southward a little farther distance in that same time. And the reason is, of course, because F is smaller, so the velocity is larger. And the vice versa happens here. If you look at the F-plane solution, you see that on the beta plane, it goes a shorter distance, again, with the agreement with what we predicted from the solution on the F-plane. And if you look at the oscillation period, it just satisfies the exact same thing. But there is no westward motion. So what exactly happens here? So, okay, so this is for the opposite case when tau is directed westward, so it's negative here. So the idea is now to analyze the equations in somewhat more, better way, okay? That's a little more fundamental way. So the first thing we do is we reduce the number of variables from A and the radius of Earth and omega and phi 0 and G and H and all that. We put it into only two parameters by proper scaling. And then the other thing, which is of prime importance, is that if you look at the beta plane, there is a conserved quantity, which is not the angular momentum, because the angular momentum exists on a sphere, but it is what I call the pseudo-angular momentum in the sense that it yields the same relationship between the northward coordinate and the eastward velocity. Okay, so if you just call it pseudo-angular momentum, there are many pseudos, but in this case, it's not the angular momentum. Define it as u minus this combination of y, the integral of f here. And you substitute in the equations, everywhere you have u, you'll substitute the d, the pseudo-angular momentum. Beta. Okay, I'll tell you in a minute. Here it is. Okay, so these are the equations non-dimensional with the two parameters, b, which is beta, and gamma, which is the wind stress, which we assume, as Ekman did, to be constant, uniform in space. And the equations look a bit messier or not much very simple, but notice that this equation is very simple in the sense that we can easily solve it. Okay, just integrate it. Gamma is the non-dimensional wind stress. Bill, here is the H. Now it's the vertically averaged. Okay, basically vertically averaged velocities. So you see that gamma, which is proportional to the wind stress, can be positive, negative, but it's not time dependent, and therefore integrating it can be very easy. So we actually have an expression for d as a function of t, and you see x doesn't appear on the right-hand side of these equations. It's what's called cyclic coordinate, and therefore the heart of the problem lies in the Vy dynamics, in which d is a parameter, that sits here and here. I'm sorry, here in the Vy and here when you want to go back to x. Okay, so B, which is the beta effect, is the normalization is such that it is equal to the cotangent of phi 0, cotangent because it's cosine over sine for some reason, I can't remember why, but it's order 1. We're at 45 degrees, it's exactly 1, 30, between 30 and 60, it's order 1. Gamma, if you put in the right numbers for the wind stress, 0.1 or 0.2 pascals, put here real numbers for rho and h take to be a few tens of meters, 30 meters or so, turns out to be much less than 10 to the minus 4. So the point is that we have here a very tiny parameter that controls the changes in the pseudo-angular momentum. So if you look now at these equations, x doesn't appear there. We can always assume that x equals 0. D can be solved into this equation, or this solution, but by a trivial change of time, just define t prime to be this, then d at t prime equals 0 is 0, so we can just use d equal to 0 at 0, and two of the initial conditions are out of the way. And the dynamics, as I said before, is actually determined by the Vy system. So we can write it as the equation of a particle in a pseudo-potential well. Okay, pseudo-particle in a potential well, where the potential well is just given by the integral of this term here, which happens to be this. I already substituted the d, which appears here, by gamma t, because it's already, we know the solution. So we have a time-dependent potential, and d squared y dt squared is equal by exactly the gradient or negative of the gradient of this time-dependent potential. So just replacing u by d gave us a classical picture, or a picture from classical mechanics, that helps us work this problem with a slight complication, that the potential here is time dependent. And still the extrema of this potential are the steady states. And the solutions or the variation about those minima of the potential are what we call the inertial oscillations. And what happens is that the inertial oscillations are very simple to analyze, and so is analysis of the roots of the derivative of this gradient here, which is a cubic equation. Okay, this is quartic. When you take the derivative with respect to y, it becomes a cubic equation. So I'll save you the details, the mathematical details. What happens is we can identify the time it takes for the potential to move away between two distinct regimes. One regime is this one, in which you have a double well separated by a hyperbolic point or a local maxima. And so a particle that starts here, okay, will oscillate about the minimum of that point. And this point itself will move slowly with time along with this point. And this point will decrease until a certain time at which there will be a change in the potential from this form to that form. We have only one minimum, okay? So it's pitchfork bifurcation, where the two minima combine to generate a single minimum, and this hyperbolic point vanishes from the system, and we can easily calculate the time as the time it takes from the minimum here to become 1/2, which is what we should expect here. And this time happens to be exactly that, 1/2 beta gamma, where beta is, or 2b, I'm sorry, is the non-dimensional beta, and gamma is the non-dimensional wind stress. So just by looking at it, just by formulating it in this way, we can immediately say, here's what we know. We know that it moves from one paradigm, okay, inertial oscillations here, to equatorial oscillations, where the particle just goes around the equator while maintaining its ever-increasing zonal velocity and zonal displacement. Okay, on the beta plane, x is indefinite. Yes, I think this is just a result of what we know, and you see the transition. Okay, so now we have a good estimate of two things. Number one, the change in the minima of the potential, or the minimum, one minimum in particular. There is another one that comes from here, and the time it gets to the equator. In the parameters chosen here, it takes 50 time units for that minimum to reach the equator. And what you see here is that the oscillation, there are two oscillations here. One, the green line is our analytic solution for the change in the location of the minimum. Okay? Once it gets to the equator, we shift again to the other minimum, which stays there all the time, so the minimum doesn't change. Of course, the u and x do change, but they're not absent from this picture, which is y as a function of time. And you see here that when we start with v of 0, when we start right at the minimum, okay, so y is 0, we start at the minimum, and v is 0, so it's not, the particle is not displaced from the minimum of the potential. Then, of course, the oscillation is very tiny. They are just due to the fact that the minimum is shifting behind it. So it starts doing those inertial oscillations, but they are very small amplitude. If you just increase the amplitude by giving it an initial velocity, then of course they have their own initial velocity, initial oscillations that is of much higher amplitude. But in both cases, the change in the location of the minimum captures the mean motion very well. And it does it both here in the mid-latitude regime and here, which is the equator. And it doesn't work well in that same region, in the equatorial region, where there's actually no frequency of oscillation. Okay, the oscillation frequency becomes undefined, actually. It becomes complex. So we are very happy with this and that. And of course, the period of oscillations can be easily tailored. Just to mention, there is the breakup of the dynamics into two elements. One, which is order one, that is the oscillations about the minimum, okay, which is actually inertial oscillations in mid-latitudes and just kind of oscillations or about the equator in the other case, and the slow variation of the potential itself, or the minimum of the potential itself. The separation of these two is part of the adiabaticity principle, which, if you look at Goldstein's, for example, one example states that when a system originates near the minimum of the potential, it will remain there at all times. Okay? And even when the potential itself changes with time, provided these changes in time of the potential itself are much slower compared with the period of oscillations. In our case, the changes in the minimum occurs with the changes in d, which takes place at the rate of 10 to the minus 4, or time scale of 10 to the 4th, in terms of the gamma. And the oscillations are basically order 1 until it reaches the equator. At the equator, of course, there is transition, so the frequency becomes 0, so this is not small. So this principle works both in mid-latitudes until it gets to the equator, and away from it along the equator with very slight range of times in which it doesn't work when it moves from one to the other. Okay, I'll spare you the details of the calculations, but we can do the same thing with the third equation, which I ignored until now, which is the zonal component. What happens now with the change or the trajectory in the zonal direction? So this was the original equation. So all one has to do, all quote unquote, it's not so simple. What happens is that if you solve it, averaging out again the oscillations, okay, you find out that the average drift, if you will, has two contributions. One of them is this beta multiplied by the amplitude of the inertial oscillations, which is determined by our initial displacement from the minimum, can be v or eta. And of course, we have to work out the terms both in y and y squared, and then take average all the periodic coefficients. And f here is proportional to gamma squared. Now, the dependence on gamma squared implies that, number one, those oscillations are completely independent of the sign of the stress. So remember, gamma is tau x, okay? So it's the wind stress that can be either eastward or westward. But this is proportional, so it can change sign. But gamma squared is independent of the sign of gamma, so the inertial oscillations are always going to be they're going to be independent of the direction of the wind stress. So somehow, miraculously, wind stress direction doesn't affect the zonal oscillations. Moreover, gamma squared, I told you that gamma is less than 10 to the minus 4. Actually, it's closer to 10 to the minus 5, but I just wanted to go on the high side. So the square of it is 10 to the minus 8. So except for very near the equator where omega 0 goes to 0, this is really, really, really tiny. Okay, remember, our non-dimensional beta is order 1, cotangent of the latitude. So it's a squared. If you are displaced from the minimum by, say, several hundreds of kilometers, it's going to be 0.1 or even 0.1. So the square is going to be several orders of magnitude larger than that. Okay, so it's number one, very small. This is a tiny contribution and independent of the sign of gamma. Okay, so here's what happened. Yeah. There is a whole bunch of oscillations that take place, okay? It goes up, you look at here, look at this one. These oscillations, this is x as a function of t. Okay, so there are oscillations. The inertial oscillations actually go this way, okay? We're not interested in them, so we want to filter them out, okay? So you average over one period of oscillation or many periods of oscillations. You take out the oscillatory part that goes up and down, or east, west, east, west, east, west, and you're left with a residual. Right. But slowly varying. So you see here what happens again in the same situation. You start with right on the equator with a blue curve, right on at the minimum with the blue curve, and you see that the oscillations are very tiny, the oscillation in x. Again, inertial oscillations only arise because you pulled the minimum below them, okay? So they're just reacting in their inertial oscillations to the change in location of the minimum. But if you start with a significant amount of inertial oscillations by increasing v, I think, yeah, v, then you see that they become, this is x, okay? So it goes up and down, moves a little bit, and then, of course, it reaches the equator, and then it goes again. In the equatorial regime, x will be quadratic with time, as I told you before, because u is linear, et cetera, et cetera. And here we have an excellent agreement. You can't see it. It's right on the money, hard to see the dashed green curve there. Okay, so let's look at a somewhat geographical portray of these things. So this is y versus x, no time in here. So this is for finite v, so we start again, or finite y. Okay? We start away from the minimum, and when you start away from the minimum, both when gamma is 0.005, when it's minus 0.005, when it's plus 0.05, then of course the direction in the north-south direction is different, but at least as long as it's in the mid latitudes, then it propagates westward, of course, until it gets to the equator, at which point the equator has its own dynamics. And of course, the change in frequency are all captured again by our intuition. This is the same thing. We see essentially the same picture, but of course, reduced amplitude of oscillations, because again, you start right on the fixed point, or right at the minimum. The radius of Earth. And here we stopped it when we got to a certain point. We didn't extend it all the way to the equator because you won't see anything here. This is terminated when it reaches close to the equator, because we know what happens here. It's huge distance and huge time. It's a long time. It depends on the parameters here. No, because I have to give an estimate for this, and I don't want to. It's a mechanistic picture. Many, many, many tens of days. Okay, so 2 pi over 10 is 60? Many tens? I stand. In terms of what? The size, the magnitude? The magnitude, you mean? Okay. So basically, you see how gamma seems to be of secondary importance in this scenario. So just to sum up the beta plane, as you see, many of the ideas developed here, both the use of conserved quantity instead of the zonal velocity and the use of the adiabaticity principle, will help us also in doing the same thing on the beta plane. But let's summarize the beta plane results. So the theory quantifies several things that we could anticipate in the F-plane results, like the transition time to the equator, which we couldn't do, very difficult to do straight from Ekman's results. Again, tau x squared is tiny, so zonal drift basically very little affected by the wind stress itself. So the wind stress, essentially, if you think about it conceptually, it just set the motion for inertial oscillations. And once you are on the beta plane, those inertial oscillations have a natural tendency to drift westward. And in fact, the wind stress itself doesn't do much in terms of their zonal drift. And the last thing I want to say is that I worked for many years on the inertial oscillations, both on the beta plane and on a sphere. And it turns out from the same model that I showed you before, you can actually get the two very differing dynamical setups. Okay, one is inertial oscillations on the beta plane. Just put gamma equal to 0, and you get the inertial oscillations exactly the way they should be with the westward drifting. We can quantify the westward drift. And if you put beta to 0, you get Ekman's results with the wind-driven dynamics on the F-plane. Okay. Time flies when you have fun, huh? Okay, so what I want to do now is apply the same ideas to the sphere. Now, the sphere is a very, very formidable beast. Okay, it has equations that really look so ugly that, well, you know, first reaction is God. No, we have to move elsewhere. So let's see how we can apply the same ideas to the sphere. And on a sphere, what happens is that you actually work with two angles. Okay, the longitudinal angle, which in oceanography and meteorology and geography, we denote by lambda for longitude in L in Greek, and phi is the latitude, which goes from 0 to plus or minus 2 pi. So all mathematicians, it's not theta, your theta is co-latitude, okay, which goes from 0 to pi, okay? But aside from that, it's basically the same spherical geometry. And these are the equations that, again, are the same type of dynamics that we saw on the beta plane. Just as I said, the equations are, how should I say it, more formidable. But notice that I put the gamma as we did on the beta plane as in Ekman's solution. They didn't make a much difference, but we put them in the zonal direction, so they are east-west. Okay, I'm not specifying the structure of this wind stress, but just that. So these equations without gamma have a conserved quantity called the angular momentum, which is again given by the analog of what I showed you with the pseudo angular momentum. This is just the radius at the latitude phi. So think about the sphere at the latitude phi. You have the local radius, okay, which is given by cosine phi, and this is the total eastward velocity at that latitude that's made up of the latitude of the velocity of a palm tree at that latitude, plus the eastward velocity relative to Earth if it's not a palm tree, but rather a wind system or what have you, water. Okay, so this is the total eastward velocity. This is R cross V, give us the direction, the component of the angular momentum, which is a vector, but in the direction of the axis of rotation. If you do the same trick and just put D, replace U, wherever it is, with this D, you get this set of equations. And what you see is that the simplification we adopted on the beta plane, in principle, works here again with uglier equations. In other words, we have an equation that is a little more complicated here for D. Lambda, which is the counterpart of X, doesn't appear on the right-hand side, so we can throw it away and consider it later on when we complete the analysis. And the V phi dynamics is the controlling element in the dynamics. Oops, that's a mistake, sorry. Lambda is cyclic, so what you see here is what happens if I write down the combined D and phi dynamics. So it's a genuine third order equation. D is not anymore a function of T only, but rather it is a function of phi, which is a function of T. So it ties in, it's related to that, to the coefficient here. So genuinely a third order system. Okay? But again, the potential here is simply given by this combination of the integral of this. We can integrate it, and it turns out to be that, d phi, okay, the same latitude, the same idea as we had on the beta plane. So if I just compare the two, okay, just put one next to the other, I'll try to finish it in 5 minutes, so David is not cross with me. And I'll do it again for constant gamma. Okay, so let's stick with the case where gamma is constant. As you'll see, many features of the dynamics are almost independent of what we choose for gamma of phi. And here is the comparison. So the expression for gamma was gamma t on the beta plane in the Cartesian coordinates, and here it's sorry. Look at this, okay? So d is a function of phi, which is a function of t. Here, t is the spherical case is just a little more complicated than what we have on the beta plane. Okay, this was supposed to be here. Sorry about that. The idea is, again, that if we look at the potential, regardless of how these change, it's exactly the same thing. Just I combined the two pictures before, and you see here that we have an expression for the time that it gets to the equator. Just the same, what I did before in two panels is here in one panel, broken up into red and blue. And what you see is this is the form of the potential, very similar to what we had before. To analyze it, I'll just do a quick run. We set the motion of the minima of the potential with the mean value of the angular momentum and its linear displacement. So these are small but very move rapidly, and these are slow, okay, but order one in terms of magnitude. And you find out immediately that this determines the relationship between the mean values of the potential and the angular momentum. And of course, once it's on the equator, it's again the same story as we had on the beta plane. dm satisfies this equation. Okay, remember that was the connection between d and phi was much more complicated than before, but still this is a doable solution. We can solve it. Again, we use the fact that gamma is very small and the adiabaticity principle. And let me run quickly to the solutions, show you what how they compare. And here it is. Okay, so we have here the oscillations. Again, this is the theory. You see the oscillations about it. This is what happens on the equator. And again, this is for tau of constant. This is the change in amplitude in mid-latitudes when you get the omega A squared has to remain constant. So when this decreases, when the amplitude or when the frequency increases, the amplitude decreases. This is the lambda phi. There are actually two blue curves in these plots. One for d itself when we integrate the equation with d, and one when we do it with the minimum, the value that's in. And you see that we're hitting very close to the results. This is, quickly I'll go over it. This is what happens when you make gamma vary with phi, like here it is the same magnitude, but cosine phi, very little difference. If we go now to the zonal direction, I'm sorry, something very interesting happens when the wind stress goes through zero, okay? So if we talk about zonal wind stress that varies with latitude, now the things become a little more juicy. You see this point where the latitude is, so the blue curves are when we start above it, and the red curves are when you start below it, below the latitude where the wind stress vanishes. Wind stress, when you start from below, it goes according to our formula here, it goes in one direction. What you see here is that at that latitude, this is phi, the oscillations increase with time, the amplitude. This is lambda, and you see that lambda can just go forever. If you start with a positive wind stress, then of course they diverge. One goes poleward, one goes southward. Okay, let me sum up, and so you don't stone me. So the spherical geometry affects mainly the marginally in terms of the complexity of the equations, but not inherently in the dynamics. Unlike the beta plane, which actually we could solve by using phi v when the potential is a function of t. Here it's a genuine three-dimensional system, but again, the adiabaticity principles allows us to treat this as a very small parameter, and look at the changes that occur in it. And again, this is the adiabaticity, slow changes in the mean state, i.e. the potential, and fast oscillations about it. And the beta parameter on the beta, remember on the sphere, we didn't have it all beta. Okay, so the beta plane is in fact an artificial parameter that comes up when we attach a tangential plane to a sphere, and suddenly we have beta that's associated with the latitude at which we attach this beta plane, this plane onto a sphere. Quickly, what can be done next? If you think about the line of meridionally aligned columns of water, again with the same wind stress, clearly the westward migration or eastward, the westward migration will be different for each column according to its initial location. So that means that we'll have horizontal divergence in the zonal direction. So the drift in the westward direction will be different for different columns of water. And the question is how fast it is, what will it do to the dynamics in the real case? Does it have any parameterization that can be helpful in the Eulerian sense? Maybe it can, we can do the same thing to generate perhaps something that maybe chokes hurricanes if it's sufficiently strong, but this has to be looked upon. And just a wild idea is that if you look at the wind-driven transport on the continental shelf, then basically the shelf provides us with the topographic beta effect. So in principle, one could do the same thing and ask, okay, now what happens if the wind blows over the continental shelf and we looked at the westward migration as migration along the shelf instead of across the shelf, and study similar phenomenon. And with that, I'm closing. Thank you very much.